Welcome to Chapter 13, Analysis of Variance, where we're going to talk about finding out if there's a difference when we look at multiple means simultaneously, more than two. Up to this point, we've only looked at two max in terms of difference. We've also just finished up looking a little bit at variance hypothesis testing. This is an extension of the two-sample tests. Now, for this, it's a little different in that we're going to be using some of the stuff that we learned with the variance side with the chi-square and F test to solve back very much like we did for the two-sample test. And we're going to use it through something called ANOVA. The first thing we're going to do is talk about a one-way ANOVA test. Pretty straightforward, the most common kind of ANOVA, where we're just looking at different sets of groups taken simultaneously and randomly assigning folks to them, and you're only seeing one potential kind of treatment. The next thing we'll look at is a two-way ANOVA. Essentially, we're looking at two things simultaneously affecting, and we're going to look to see how that works. We call it no interaction. And the third one we look at is a factorial, but we're going to call it a two-way ANOVA test with interaction. That's what we use in Excel. So what do we do with ANOVA? Well, let's take a look. So for this case, how much does using public transportation save? And what they have are four different cities: Boston, New York, San Francisco, and Chicago. And you can see the four different mean amounts that are saved in each city. And the samples of each were 5 in Boston, 8 in New York, 6 in San Francisco, 5 in Chicago. And you can see the sample standard deviation of each. Notice the standard deviation of each. And we're wondering whether or not they're the same. Can we, now they all look to be different. They're not, the means are not the same. But the question is at least one of them different? Chicago's looking a little bit different, however, it has the most standard deviation. I want to know if we can find that they're all the same, or by rejecting that notion of they're all the same, can we find at least one is different? So let's start with the one-way ANOVA. This is the basic ANOVA that we'll see, and we'll use this again in regression. We want to look at 3 or more populations at the same time. Now you can use ANOVA for two-sample as a t-test. You can test it, but really is intended for 3 or more. We're looking at one particular object that we're looking at as the overarching theme. And if you think of it this way, imagine that it's this overarching theme and we're getting multiple treatments that are different within that stream. So what we would do is use something called completely randomized design, where we're taking and randomly assigning people within each bucket. It's not deterministic, it's completely random. And then we're going to take a look at the means for each of those treatments and see if the treatments underneath the overarching factor have a one being different. So three things have to be talked about here to start. What are some underlying assumptions? Well, the first assumption, and this all goes back to when we talked about the two population differences, you assume that underneath it all, the populations are normally distributed. That's a basic understanding of much of statistics, and when they're not, then we see some kind of difference happening and we get rejected nulls. We're also going to assume that the population standard deviation, the sigmas, they're unknown. Remember when we did the t-test of difference, unknown sigma? We're going to assume they're unknown here, but we're going to assume that they're equal. And you can take a look at this, and we will look at the variances and the standard deviations, and you'll be able to see that while they may not be exactly the same, they're going to be pretty close. We just got done looking at the variance tests, and now as we move into this, you'll get a better flavor for it. Also, when we pull these samples, they're going to be selected independently, so be clear on that. So we're looking at least three populations when we pull out, rather than 2. We'll call it C because what we're going to do is compare more than 2. So we're saying all the means are the same, or at least one is different. You don't want to say all population means are not equal, because that means that they're all different. You can either say not all population means are equal, or you can say at least one population mean is different. If they're all going to be the same, they'll fly under one flag and all the means will be tightly bound around what would be assumed one singular population mean. If we had the unique circumstance, you'd have to test this multiple times then with t-tests. Once you've figured that you reject one and find at least one is different, you could have them so far apart that you can actually see the difference in the population distributions. What we want to prove is at least one of these four, if that's our goal, is to reject the null and find at least one of those four is significantly different than the rest. So for this, what we'd like to do is start with the variability that happens. So if you think of our data, well, let's just take a look. Let's take a look at the data. And here's just a random set. Here's that data for Boston, New York, San Francisco, and Chicago. I want you to think about ANOVA as columns and rows. So for this kind of single factor, completely randomized design, what we're going to do is assume that each one of these columns exists on its own and everyone's been randomly assigned to it. What we're going to find is, if we just bleed back to this, that we're going to look at the between values. So I want to look at the variation that occurs between them. So what's happening between the columns? Then we're going to measure what's happening within the columns. So when we talk about what happens between the columns, that's very important because for us, that allows us to see as we move this forward, we're going to have a between measure of variation. You will often see it referred to, especially in Excel, as you see my cursor move over between groups. The other one, the within, is what's happening within each column. That is kind of just random error or white noise. Once we find those two, we're going to take the ratio of the between over the within, and that'll be our F statistic. They're both separate variances like we saw with the F distribution when we did the variance test. Now that ratio will be used again, and we'll be able to use the F dist to find out the p-values. What's important to know, though, is that we're focusing on some means here. Each of the columns will have a mean. Each of those columns will have a mean we call X bar. X bar for column 1, X bar for column 2, X bar for column 3, and so on. In addition to that, they'll have a grand mean. Notice it's X with 2 bars. It's the mean of means. It's the overall mean of everybody. So here in this data set that we have, Boston, New York, Chicago, I know that there's 5, and I'll put this sheet out for you to take a look at. I know there's 5 people from Boston, 8 from New York, 6 from San Francisco, and 5 from Chicago. I know that the mean of each one of those is here. I also know that the total mean, everyone, has a value. So essentially, you're just lining them all up and taking one grand mean. And that grand mean is important because it helps us create variance. With the sums of squares due to the treatments, as I said, overarching, there's a theme. We often call it a factor. Within the factor, there are treatments. So Boston, New York, San Francisco, and Chicago are each a treatment or a level. What I'd like to do is create a sums of squared. Sums of squared. Notice I'm summing the squared deviations. When I sum the squared deviations and take it on average, I get a mean square due to treatment. The mean square due to treatment is our variance, much like we've seen with S squared and sigma squared. The SSTR, the sums of squares due to treatment, very rarely do you have to actually calculate that value in a brute force manner. Excel does it for you. If you're expected to do it in a course, it's usually just a simple backed into ratioed number. But I want to give you a sense of what it looks like. Let me blow this up a little bit. What we're going to do is take the value of the count. So what I'd like to do is take the mean of that column, subtract away the mean of means, and square it as we're supposed to. That's what's happening here. Then I multiply it by the number in the total so that I increase it so that it looks like each one of them is contributing. So it's kind of a compounding factor that I want to use. I get 5 times that squared deviation. And I'll do that for each one. And when I'm done, I get the total amount of sums of squares that have been compounded by their counts. That value is called the sums of squares due to treatment, and you see it here. If I want to get the mean MST, as we see it here, MSTR, mean squares due to treatment, I'll take that number and I'm going to divide it by the total number of, as we see it here, those cities we can often call within that group, we call them treatments. We have a total of 4 minus 1, and that's how I get a value for the mean square due to treatment. This is variance. Mean squares due to treatment is a variance number. That number is the numerator to the F statistic we'll calculate once we generate the mean square due to error. Here's how it will be done just looking at it mathematically. You saw me just prove it right here. So the last piece before we roll through this is the sums of squares due to error. This is often a backed into number for us when we have it in an ANOVA table, which you've kind of seen it off to the right here. But it's a backed into number most often. But you can also calculate it by taking a look at the variance of each column. Each column has variance. And then I'll multiply each of those by their individual degrees of freedom, the count in each column minus 1 times it, and then I'll divide by the total number of treatments, total number n we have, minus the number of treatments, so the total sample size minus this value. This is a backed into number most often. It can be calculated and it is calculated on the sheet. So you can see how it's done here. 5 minus 1 times the variance plus 8 minus 1 times the variance standard deviation squared, and it gives us our sums of squares due to error. The mean squared error, which is our white noise variance, is what I can't explain. The treatment is basically of the total variance, and that totality is just nothing more than the variance in total of everybody, regardless of what column you're in. The mean squared due to treatment is the amount of variation that I can explain because the treatments are telling part of the story. The mean squared error is the variance that I can't explain. So now that I have all these pieces, I have the variances taken care of. So my hypothesis is all the means are the same, or at least one is different, or not all means are equal. I calculate the treatment mean square, the error mean square, take their ratio. I know the 2 degrees of freedom that I have, the first and the second. Notice the second and the first together, when added, get you to n minus 1. This plus this is n minus 1. We know in total how we get the F dist. So when we run something like this out, let's take a look what happens. There's a unique function that we have in Excel that allows us to create this, and you see what I have creating an ANOVA single factor. What we'll do is go into data analysis from the analysis toolpack, ANOVA single factor, and what I'll do is I'll highlight all 3, and they don't all have to be the same count. Notice they're different, only 2 are the same. I labels in the first row. I'm going to test this at say 5%. I'll put it right here and I'll click OK. What you get is an ANOVA table. Here are the same counts. They match up to what we have. Notice my mean here matches up here, here, and here. My variance matches up. The sum, you can sum them up. It's unimportant for this. But you'll also see that I get my sums of squares due to treatment. So this is your treatment. But this is your error. and you get this wonderful table. So what happens with this ANOVA table, it's important to know, it sums down in the sums of squares column and the degrees of freedom column. However, that's where the summing stops. You can't sum up your variances. You can only say, that's the amount of variation that I can explain. So to get the mean squared due to treatment, I would simply take the sums of squares divided by the degrees of freedom. This is given to you. I'm just showing you how easy it is. This is how we clear the table. Sums of squares due to error, degrees of freedom divide by. Notice there were 24 observations, minus 1 is 23. There were 4 different treatments or levels. Minus 1 is 3. 23 minus 3 is 20. Now that I have my mean squares, the F statistic, or the F value we get, is the mean squared of the treatment over the mean squared of error. And ultimately, the F statistic can lead me to an f.dis.right tail. I'll put in the F value. I have the degrees of freedom for the treatments, the degrees of freedom for the error, and I get a value basically that is 0. So by finding a value of 0, I'm rejecting the null. Remember what we have here. Let me go back a second. I'm rejecting this null, and I'm saying at least one of them is different. I can tell you which one just by looking at them, but the goal of this test is just simply to reject the null and say, hey, look, if you thought they were all the same, they're not. And there's good and bad parts to this. In some cases, you want them all to be the same because it shows a measure of homogeneity and things are all the same. But if you reject the null, what you're saying is, hey, you do have something different occurring somewhere. Now you can go in and do separate t-tests. So with that, I just showed you how to do all this, how we can do it in here. I have another one on this sheet that you can see, and we'll look at that here in a second. And I also have several other older videos showing multiple ANOVAs that are being done for you to view, and it should give you some guidance. So, no interactive two-way ANOVAs. Again, it's easy to do in Excel. What we're going to do, 2 factors. Before we saw 1 factor, multiple levels or multiple treatments. So imagine the columns, each column represented a particular treatment. Now turn it to the side. In addition to having that, imagine the rows could serve as their own levels. If you had three columns and 3 rows, you could see that we could actually have multiple, maybe 3 levels or 3 treatments in the row side. You want to see whether or not there is this effect happening if a brand of a hybrid car and the octane level influence gas mileage. So is there's the combination of 2? What we want to see though with this no interaction is we often call this blocking, where we take something in a column and express it across all 3 of the columns. So one row has an object and it gets tested across all 3. So normally with an ANOVA that we've seen, say you have something like this, student trying to decide what career to pursue, you're trying to figure out their salaries, these are in thousands of dollars, which one would you go into? Well, here we have them. Here's that data set. I took each and got the mean for each. And with that, I went and ran a single factor ANOVA. And I went in and said, hey, look, I did the data analysis, I did a single factor ANOVA, I took my data set over here, I highlighted all my columns, found a place to put this over here, wonderful, and I got this result. Now, from this, what we've just seen is a p-value greater than 5%. So in this case, we wouldn't reject the null and we say, hey, you know what? All the means are equal. They certainly don't look equal here, but the reality is statistically, based on the fact that the med also has the highest degree of variance, their grouping is not significantly different. Yes, they're different. No one's going to argue that, but they're not statistically significantly different. That's key to all this. But what if we took another step back and said, does the level of education, so if you take someone at a high school, so high school seeing all three treatments, bachelor seeing all three treatments. I'm not randomly assigning them anymore, particularly under each column. I'm forcing it through to each column. It looks like as your education level goes up, you tend to make more money. Now, the question would be, is it the employment, the field you're in, or your degree that seems to be pushing this? You can see the average for each. So the average education was 43,500, 54,500 for financial, and medicine was 60,250. But you'll also notice that PhDs make 91,670 versus 23,000 for just high school students in general. The mean of means, the grand mean, was $52,750. So this is not your typical one-way ANOVA because it's not just one way. It's two ways. We're looking down and now across. So high school is going to see all three, bachelor's is going to see all three, master's is going to see all three, and PhD is going to see all three. It looks like education has the biggest impact. We already did the one-way ANOVA and found that, hey, there's no difference here. The question is there a difference here? So what I'll do is use this thing called the randomized design or randomized block. It allows the individual row header to see all three columns. Back to it. Here it is. I have taken this data set, put it into Excel, and now I'm going to run the data analysis on this. It's ANOVA two-factor without replication. So what it means is you're only one high school is seeing all this. Imagine if there were multiple high school, multiple bachelor. It's not a repeated value. So I do it without replication. I'm going to cover everybody, all the titles, and I'm just going to put it over here somewhere just to get it out of the way. And I'll have a nice ANOVA that's run. It should match the one we have already. We'll take a look at the one I have here first, just so you can see it. And I see that the averages line up. Here are all the averages for the rows. Here are the averages for the columns. And I get this ANOVA table. Well, let's just think about this. The ANOVA table is going to have rows, columns, and error. Now, the rows are often called blocks. That's why it says SSB. So, row variability, column variability, which usually we call our main effect, but it is one of the two main effects in this case. And we still have this thing called white noise. Now the variance is very interesting in the ANOVA table. The variance, now look what we're doing here. If I blow this up a little bit, if I take and say what is the total variance of this sample, and I say there were how many in each, how many in total? Well, there were 3 by 4 is 12. If I say, what is 12 minus 1? And I take the total variance times 11, and I come down here, I see that this number, sums of squares total that I got from running the ANOVA, is nothing more than the total variance multiplied by the sample size minus 1. Very interesting. And remember, sum down, that's it. Now we take this divided by this divided by this divided by this, and get all of these. What we'll do is use the error term here as the basic benchmark and say the mean squared for the rows, which is the block, divided by this error value. And I'll do the same thing for the column, divided by the white noise. And then I can get the p-value for each. Two separate f values, two separate p-values, one for rows and one for column. At 5%, both of them are less than 5%, so we reject the null. And what that does for me, it says that at least one of the rows is different and at least one of the columns is different. Now before, when we ran some data, it didn't look so nice. But now that we have a different view of the data, this data set is not the same as this data set. This is a completely randomized single factor where we took 4 people randomly from each field and put them in. This was a collective look at high school, bachelor's, master's, and PhD. But what have we proved? We've proved that at least one of the education levels is different than the rest, most likely PhD. And we've also proven that at least one of the fields is different. So most likely this is different, and most likely this is different. We could then run and induce separate t-tests to determine which one it really is. But it's knowing what is the block. So the row is the block, and the column would typically be our original or main effect. Now, when we look at this, we have one thing to do. That is, wonder what happens if we have repeated values within each of the blocks. Well, that creates something called interactive effects, or an ANOVA with interaction. So now we'll have the row, the column, and then an interaction that's occurring between the columns as well as the white noise. So interaction, it says, means that the effect of one factor is statistically dependent on the level of the other factor. So one has a dependence on the other. One moves in the direction of the other, right? So perhaps education impacts salary in the financial sector, but it doesn't in the professional sports. So in the two categories, employment and education, they interact differently depending on the level or the sector. So there's a difference happening. One has a different effect on the other than the other. Back to what we had before. This was what we had just seen. Now, what happens if we take it a step farther and we have multiple high school and multiple bachelor and multiple masters and multiple PhDs, so that we're able to see what happens through repetition of each of the education levels across. Now, what I'm looking to find out is, can I see an interaction happening at the education level on the effect of the field of employment factor A? Now I need to make sure that each of the repeated levels has the same amount of repetition. So if you have 3 high schools, make sure you have 3 bachelors, 3 masters, 3 PhDs. That's an Excel quandary that comes up a lot. You can have different levels, but when we use it in Excel, it has to be the same number. So what if we tried this? I'm going to pull the data out here. Here it is. 3 high school, 3 bachelors, 3 masters, 3 PhD. What I'm going to do is run 2-factor with replication, highlight everything as we did before. I'm going to have 3 rows, or three within each level, 3 objects, and I'm going to put it out here. I'm just going to click OK. You get this summary statistics for what happens for a person in high school, someone in bachelor's, someone in PhD and master's. And you'll see also that we have the total counts. Now the main effects, education, financial, medical, aren't being handled the same way here. What's important is to come down to the ANOVA table. You have your sample, column, interaction within. But let's just make sure we know what this means. Excel changed terms on you. It's not a good idea. Interaction makes sense. But within is always our error term. The column is our factor A, often called main. And then the sample is our factor B, and this is the repetition. This would be our interaction, obviously, it already says that. Each one of them has sums of squares, degrees of freedom, mean square, F, and P values. Now, if we go and take a look at this, again, all 3 of them are less than 5%. So as we saw previously, they're less than 5%, we're going to reject the null. So rejecting the null of the repetition means that at least one of the factor B levels is different than the rest. At least one of the main effects, in this case, one of the different fields is different than the rest. And now we have interaction. We have a rejected null of interaction. You would love it if it didn't, because then you can just say there is no interactive effect. There's not something goofy going on. Now ours is just to get started in ANOVA and have just an introduction. And there's more to this to read, but if the output indicates something interaction is significant, then the main effect is a little bit complicated when you explain it. So here's just a quick outline. When we have a significant interaction, we say interaction means that the independent variables are not really all that independent. Well, they have some level of dependency. One is sort of depending on the other for its movement. But more importantly, the main effects, those things that you initially thought could tell the story, can't be relied to tell the whole story. You know that what's coming out of factor A explains some of the variation. What's coming out of factor B explains some of the variation. You know error is what you can't explain, but there is additional piece out there that can be explained between A and B. That's more than what A and B could tell on their own. That interaction between A and B is what we have to do. And I have a little picture here. Hopefully you can follow this. This is a very common one. I pulled this from an old stat book that I had years ago. And we're looking at when you sleep in the morning or the evening. And the orange line would be morning and black line is evening. And I have some overlay. And it's doing exercise, doing light exercise all the way to heavy. But essentially, you're either doing light activity, just milling about, going for a short walk. Heavy is going to the gym, working out, doing CrossFit, something where it's a lot more strenuous. So if I measure them and I look at the line, the span of the line to see whether or not people get the same amount of sleep, really, in this case, nothing significant is happening at either end. We're not seeing much of a difference. So there's no significant effects. If we see that, for example, morning sleepers get a lot more sleep than people who sleep in the evening, but their light to heavy low doesn't really change, basically the time of day has an effect, and that's it. So time of day has an effect on when you sleep. Here, there was nothing affecting what you were sleeping. The next one, C, says the difference between light and heavy. Basically, there's a significant intensity of exercise effect, but there's no difference in morning and evening. Here, we're beginning to see a difference between both light and heavy, so we see a significant intensity for both, and the time of day has an effect, but they're not interacting. Here, next one, we see that for someone, as they're increasing in their morning sleep, they tend to sleep more after heavy exercise, but people at night tend to sleep less. This has a significant interactive effect, but there's no other effect. The only thing that goes on is some measure of interaction that can't be that's happening, and we need to find a way to explain it. This has significant interaction. Here, the last one, F, is challenging. Notice there's a difference. There's a split between morning and evening. So the time of day has a significant effect. But also notice that the pitches run almost counter to one another, but they don't intersect. But it is an interaction. Notice nothing's happening between here and here for evening sleepers, but morning sleepers, it seems the more you work out, the more you sleep. So there's a time of day effect, and there seems to be an interactive effect between light and heavy occurring for one and not the other. As I said before, it's happening in one but not the other. That's how we see the interaction. Part F is the one that most of us see would be the challenging one that comes up the most when we reject the null and find out that there is a significant interactive effect. So when you do reject, think about part F over here, that one of them is moving in a way the other, and there's already a significant separation. So there is an effect for one, but not the other. Just a general overview of Chapter 13. Chapter 13 leads us from ANOVA into regression. And the heart and soul of regression is a general ANOVA table. Leave it there. We've got some work to do. I will have additional videos on how to do some problems, and we'll see you in Chapter 14.